today's video, I am going to explain uniform continuity. According to the definition of uniform continuity, let S be an aggregate and F maps from S to R be a function. We say that this F is uniformly continuous on S if for given epsilon positive greater than 0, then there exists a delta greater than 0 such that x1, x2 belongs to S. Then modulus of x1 minus x2 less than delta, which implies that modulus of f of x1 minus f of x2 less than epsilon. So this is so easy to remember. If it's continuous, only single value will be there, and here 2 points are there for uniform continuity. S be an aggregate and f maps from S to R be a function. Then we say that f is uniformly continuous on a point, yes. If for given epsilon greater than 0, there exists delta positive such that x1, x2 belongs to S. Modulus of x1 minus x2 less than delta implies modulus of f of x1 minus f of x2 less than epsilon. So this is according to the uniform continuity. So here, based on uniform continuity, there is a theorem here. So what is this theorem? If f maps from S to R is uniformly continuous, so we have to prove that f is continuous on S. So here, when comes to the theorem, so THEN then plays a vital role. So before then it was given, so the statement is given, f is uniformly continuous. So after then we have to prove that. So what is it we have to prove? That f is continuous on S. We have to show that f is continuous on S. And according to the uniform continuity, we have the definition here. See here. So what is given? F is uniformly continuous is given. So given, see, f is uniformly continuous on S. Then according to the definition, we have then for given epsilon positive, so given epsilon greater than 0, there exists delta positive such that, so I am taking 2 points here, that is x comma y. So this is x comma y belongs to S, which implies, that is comma 0 less than modulus of x minus y less than delta, which implies that modulus of f of x minus f of y less than epsilon. So claim, what is it we have to prove that? So the claim here is, so we have to prove that, after then we have to show f is continuous on S. So we have to show that, to prove that f is continuous on S. See here. So how we have to show that f is continuous on S? Let, see here, let A belongs to S. On taking, in place of y, I'll take A. So which belongs to S. So in place of y here, from the definition of uniform continuity, in place of y, I'll take y. Y is equal to A. Then see here, the same statement I am writing. Then for given epsilon positive, see here, given epsilon positive, there exists a delta positive such that, see here, such that x in place of y, what I am taking here, y is equal to A. In place of y I am writing A, that is 0 less than modulus of x minus A less than delta implies modulus of f of x, see here, f of x minus f of A. So minus f of A less than epsilon. So this is nothing but the definition of continuity. Therefore, f is continuous. See here, according to this definition, f is continuous on A belongs to S. Since A is arbitrary, since A is an arbitrary value, so f is continuous. See here, f is continuous on S. See here, what is given? F is uniformly continuous is given. So according to the uniformly continuity, we have epsilon positive, there exists delta positive such that x1, x2 belongs to S. Modulus of x1 minus x2 less than delta implies f of x1 minus f of x2 less than epsilon. So the theorem according to the uniform continuity is f is uniformly continuous is given. We have to show that f is continuous. So what is given? F is uniformly continuous on S. Then For given epsilon positive, there exists delta positive such that in place of x1, x2, I have taken x comma y belongs to S, such that 0 less than x minus y less than delta implies f of x minus f of y less than epsilon. So what is the claim here? To prove that f is continuous. See, after then we have to show f is continuous on closed AB. So in place of y, I am taking A. So here this is the step which you have to keep in mind. So A belongs to S and y is equal to A have taken. So in the same uniform continuity step I am taking in place of y as A. So this is nothing but the definition of the continuity. F is continuous on A belongs to S. Since A is arbitrary, we say that F is continuous on S. So here one thing you have to remember is the converse of the theorem need not be true. The converse of the theorem. What is the converse? Converse of the theorem need not be true. So it is so important, is need not be true. So what is the converse of this? We have to consider f is continuous and f need not be uniformly continuous. See here, for uniform continuity, so we have to suppose that f is continuous. Suppose that f is continuous on S. F is continuous on S. So according to it, the converse of the theorem need not be true. So I am considering f of x is equal to 1 by x. For example, I am considering f of x as 1 by x. Clearly f of x is continuous. Clearly f of x is continuous on S. So f of x is equal to 1 by S is continuous on x. So now for epsilon positive, we have to choose delta positive such that, see here, 1 by n is less than delta. Let x is equal to, I am choosing x value as, so I am choosing x value as 1 by n and y value as 1 by 2n. See here, now I have to consider modulus of x minus y. So which is equal to, what is x here? This is 1 by n, and what is y here? This is 1 by 2n. So if I make a LCM here, so this will be 2 minus 1, so which is equal to 1 by 2n. So which is less than delta? So 1 by n, it is less than delta here. So 1 by 2n is less than delta. Now I have to consider here modulus of f of x minus f of y. So this will be, what is f of x here? So f of x is nothing but, see here, f of x is nothing but 1 by x. Now, so this will be 1 by x minus 1 by y. So what is x value? So x is nothing but 1 by n. So this is 1 by n. This is 1 by 2n. So this, the reciprocal of this will be n minus 2n. So n minus 2n. So in modulus it will be capital N. So n, how it is? So here if you observe this one, 1 by n is less than delta. So we have 1 by n value as less than delta. So if I reciprocal it, n value is greater than 1 by delta. So 1 by n, we got the value as greater than delta. So this value we got as greater than delta. So we have to choose that. Choose delta positive such that delta is equal to epsilon. Now f of x, modulus of f of x minus f of y, we got, if I choose delta is equal to epsilon, so we got the value as greater than epsilon. So which is not, therefore f is not uniformly continuous. Therefore f is not uniformly continuous. It is not uniformly continuous. If it's uniformly continuous, it should be less than delta. So we got f of x minus f of y is greater than delta. Therefore f is uniformly continuous. So if f is continuous, then f need not be uniformly continuous. So converse of the theorem need not be true. Uniformly continuous. So this is the theorem on uniform continuity. See here, according to the uniform continuity, for epsilon positive there exists delta positive such that x1 x2 belongs to S, such that modulus of x1 minus x2 less than delta implies modulus of f of x1 minus f of x2 less than epsilon. So we took f is uniformly continuous. In place of y, I substituted a, and it's the statement of continuity. Then we said that f is continuous on S. The converse of the theorem need not be true. So now we have to suppose that f is continuous on S. So suppose that f is continuous on S. So we have to show that f is uniformly continuous. So for example, I have taken f of x is equal to 1 by x. Clearly f of x is continuous. So according to the continuity, so I took epsilon positive, delta positive such that 1 by n is less than delta. So n will be greater than delta. See here, then n is equal to x I have chosen as 1 by n, y I have chosen as 1 by 2n. So here the value here will be, so 1 by n, so 1 by n which will be 1 by 2n is less than delta. So again, according to the uniform continuity, I have to choose modulus of f of x minus f of y. After substitution, I got this value as greater than epsilon. So which is false? So which is not uniform continuous. Therefore, according to this statement, if f is uniform continuous, then f need not be continuous. So f is continuous. So if f is continuous on S, f need not be uniformly continuous. So this is the theorem on uniform continuity. Thank you so much for watching and staying till the end. If you really like, you know what to do, please practice.